Hey guys, Kenna here. Today we're going to go ahead and talk about how to do ray tracing diagrams or ray diagrams for concave and convex spherical mirrors. Okay. Now, the basics of these processes are going to be good because you can apply them to both types of mirrors, and we can go ahead and look at them as a starting point for when we go ahead and do lenses as well. Now, we're going to go over some basic terminology of how these work. Then we'll go ahead and give you some basic rules. And the nice thing about this is that the rules that we're going to go over today are basically true for both concave and convex, even though they play out a little bit differently. And they'll actually hold up pretty well as far as doing lenses as well when we go ahead and get to lenses. We're not going to talk about lenses in this particular video. We're going to go ahead and focus on the mirrors, but you'll get the idea hopefully as we go through. Now, before you go ahead and get started, I would go ahead and make sure that you have a really sharp pencil or pencils. I like doing some of these basic ones with colored pencils just until you get the idea of where each ray comes from. And then make sure that you have a straight edge. You should have your protractors that we've been using in class. So go ahead and make sure you have those out before you go ahead and get started. Okay, so let's go ahead and jump into some of our key terminology. We'll start with the center of curvature. This is typically going to be labeled as C, and in a spherical mirror, the center of curvature is the center point of the hollow sphere of a mirror. In a concave mirror, the center of curvature is in front of it, but in a convex mirror, it's going to be behind it, and I'll show you that when we actually get to our diagrams. Okay. The next term is what's called the pole. The pole is the center point on the spherical mirror where it crosses what's known as the principal axis, and we'll go ahead and talk about the principal axis here in a minute. The radius of the curvature is the next one. Now, just like any other radius, we got to think about this as the distance from the center to the actual outer rim. Okay, and so if the center of curvature is C, the distance from C to the mirror is going to be the radius of the curvature. Then we get to the focal point. Now, the focal point is the point at which the light rays of the mirror focus on the principal axis. We label the focal point F, and if you are not given F in a particular setup, you can find F because F is 1/2 of C. Okay, it's halfway between the mirror and the center of curvature. The last part is the principal axis, and this is the straight line you'll typically see that's going to pass through the center of the curvature and go ahead and strike the pole. Now, this is typically what we would consider to be the line of sight with respect to the eyeball or whatever the viewing object is. Okay. Now, let's go ahead and talk about some basic rules that we're going to go ahead and use for this. But in case you haven't seen kind of a spherical mirror of some sort, think about like those garden globes that they have that you can kind of that are mirrored so you can kind of see around the garden. They look a little something like this. Okay, this is kind of what you should be envisioning when you go ahead and think about, oh, that would be a nice convex mirror. Okay. Now this is obviously 3 dimensions and it obviously has some curvature left to right as well as up and down. For our examples that we're going to be doing, we're thinking of a thin slice. And so we're really thinking about the curvature going up and down, not necessarily thinking about it left and right, but you can extrapolate it to go ahead and include an example like this. All right. So let's go over the rules. Now I'm going to give you 4 rules here, and they're essentially going to be the same for both concave mirrors and convex mirrors. When we go ahead and start taking a look at this, however, you'll see that rule 4 is going to be in red. And the reason for that is if you get 3 rays dialed in, you should have a pretty reliable answer. Then ray number 4 should be just a good way to check yourself if you feel like you need it. In theory, you could even do this with 2, but it's always good when you're especially learning how to do this to use at least 3 rays to go ahead and make sure that your point at which they cross is consistent from one to the next. Okay, so here we go. So for concave mirrors, this is where we'll start with. Rule number 1 is when a ray of light, which is parallel to the principal axis, gets reflected, it's going to pass through the focus. And we'll go ahead and show you that when we get to our diagram. Rule number 2, when a ray of light passes through the center of curvature, it's reflected back along the same path. Rule number 3, when a ray of light passes through the focus, it comes back parallel to the principal axis after reflection. And again, rule 4, and this is if necessary, if you're having trouble or you're unsure about the results you've gotten, you can go ahead and do a ray of light which is incident at the pole. Remember, the pole is the point at which the mirror crosses the principal axis. So at that point, if you're going from the viewing point to the mirror, remember that with reflection, angle of incidence is equal to angle of reflection. So as long as you make the same angle coming back out, you can get one more ray. This you would definitely want to go ahead and use your protractor for, to try and make sure that those rays are even in terms of their angle of incidence versus reflection. Okay, so let's go ahead and jump right in. Pull out your diagram. You want to go ahead and start with your concave spherical mirror, and we'll go ahead and take a look at this. Now, the arrow that you see here is going to represent your object. You could really use any object. This just makes it easier to give us a starting point from which to go ahead and put our light rays. Now, there is a dot there, and this is going to be the center of curvature. And because this is the center of curvature, that means the distance from the center of curvature to the pole of the mirror is the radius. This is the radius for the curvature of the mirror. Okay, this one does not have F identified on it, so no focal point. So we're going to do the focal point, but remember the focal point is 1/2 of C. So the distance between C and F is the same between F and the pole. And this distance from F to the pole is known as the focal length. All right, so now let's go ahead and start drawing our rays. So if you're using just black and white pencils, just regular pencils, that's fine. Just make sure it's sharp and you're ready to go and have your protractor ready. If you're using colored pencils, pick your first color and then let's go ahead and get started. I'm going to do my first one in blue. So we're going to draw it. The first ray is going to always come off parallel from that starting point, and I'm going to go ahead and begin at the very top of our arrow. So I'm going to run parallel to the principal axis and strike the mirror, knowing that after I do that, it's going to come off and go through the focal point. All right, so it strikes the mirror, goes back off through the focal point. So we've now drawn our first ray. Now for me, I like to go ahead and do the ray that goes through the focal point next. So I'm going to go ahead and start at the same point. This time I'm going to go through the focal point, and when I strike the mirror, I'm going to come off parallel to the principal axis. So that comes down, strikes, and bounces back out parallel to the principal axis. Now, you should at this point already have some idea of where the image is going to fall that it produces. In this instance, the two lines, okay, both of the outgoing, go ahead and connect at a point. But just to make sure we're on the right track, I'm going to do that third line. This time I'm going to run through the center of curvature. And because we're going through the center of curvature, it's going to hit the mirror perpendicular, which means it's going to bounce straight back to the same point. So when you draw this one, you typically go ahead and draw arrowheads on both sides. And now we have a pretty good idea of where that image should be. So I'll go ahead and put that image in. Okay, so you'll notice that we can now tell a lot about what this setup is going to do from the mirror. Anytime you do a ray tracing diagram, you should be able to speak to the image's location, size, orientation, and type. Now, if you're not sure what I mean by orientation, I'm talking about whether it's upright or inverse. Okay, so with this particular example, you'll notice that my arrow is upside down. So this would be what we would call inverted or inverse. Okay. This particular one is located between C and F, so between the center of curvature and the focal point. It's going to be diminished in terms of size. It's not magnified. It's not the same size. It's actually shrunk down a little bit, so it would be diminished. And because you have solid lines that are going to go ahead and converge on this point, this would be what we would consider to be a real image. Okay, so let's kind of go over that one more time just to make sure you're following along. So the first thing we want to go ahead and do is make sure that we're all clear on what it is we're trying to go ahead and identify. So those things you should be able to do are our location, and in this particular instance, we're between C, the center, and F, the focal point. We should be able to go ahead and do the size. It is diminished in that it is smaller than the original object. We can go ahead and do orientation. In this particular instance, we are going to be inverted. It's upside down. And then lastly, we have type. And in this particular instance, we're dealing with a real image because the light rays actually converge. Okay, so each time you're going to want to go ahead and do location, size, orientation, and type. Okay, and this will be able to get in a pattern, and you can go ahead and feel pretty good about that. Now, on the previous slide, when I was going ahead and giving you the rules, there was one more rule that we said we could go ahead and do, one more ray that we can go ahead and create. This one's a little harder and will require you to go ahead and use your protractor, but essentially we're going to go to the pole. Now remember, the pole is the point at which the mirror crosses the principal axis. So if we go ahead and draw that one right now, I'll do it in a different color again. It's going to go ahead and come in, strike the pole, and bounce back out. And you'll see that once again, these all pretty much line up in the same spot. Now, what if yours don't? Hopefully they're close enough. And if you're really exact as you're going through and being really honest with yourself with your protractor, you should get a pretty good result. Even here on the computer, I'm getting a decent overlap of these different lines. And so I know my answer is pretty close. Okay. Regardless of how little it may be off here, all of the things I wrote up above are going to be true. In this case, it's still diminished, it's still inverted, it's still real, and it's between the center of curvature and the focal point. And it turns out that this actually is common for any ray tracing diagram that you do where the object is outside of C. There are some special instances with these concave spherical mirrors where it's not exactly like this. If we go ahead and put the object right at the center of curvature, you're going to see that the actual image is going to be right at C. It's going to be inverted still. It's still going to be real. But in this time, instead of being diminished, it's actually going to be the same size. If you then go ahead and put your object in between C and F, you're going to go ahead and see that the image that you produce is going to be past C. It will be enlarged or magnified. It's still going to be inverted, however, and it's still going to be real because there are real light rays converging together at that point. Okay. The other instance we typically look at is between the focal point and the mirror. Now, this one gets a little tricky, and I'm not going to go into this particular example. I'll have you go ahead and try it at some point on your own. It may make more sense how to do this one after we go ahead and go over convex mirrors. Okay, so hopefully you've seen that. The first ray that we drew was parallel, and then it went through the focal point. The second ray that we drew went through the focal point, then came off parallel. And the third one went through the center of curvature and bounced straight back. And if you need to check yourself, there you can always do one that goes to the pole and then comes back off at the same angle. So angle of incidence, angle of reflection. All right. Okay. So when we go ahead and take a look at these, hopefully you're getting a better idea of how to do this. I know it's better to do it in person and on paper, but this is what we've got. So I hope this helps you understand it better. Now, again, I want to point out too that the eye is viewing as if it's coming from the left and the mirror is on your right, making this a concave that you can walk into. Okay. All right, so let's go ahead and take a look at the rules for convex mirrors and then go ahead and do an example of a convex mirror. All right, so rule number one, after reflection, a ray that comes in parallel to the principal axis comes back through the focus. Sounds very familiar? Hopefully all of these should, because they are the same rules that we had for the concave mirror. Rule number two, a ray of light goes towards the center of curvature, is reflected back along the same path. Rule number three, after reflection, a ray of light going towards the focus becomes parallel to the principal axis. And then if you need to check yourself, you're unclear or you're having trouble with one of the others, rule number four, a ray of light which is incident at the pole is reflected back, making the same angle with the principal axis. Angle in equals angle out. Okay, so let's go ahead and try doing the same sort of ray tracing diagram we did before, this time for a convex mirror. So again, you'll notice that the mirror is bowed toward us this time instead of away. And so you can't walk into the cave. That makes this a convex mirror. But again, look at the eye. The eye is on the left side, and so we're viewing it from the left. And your object is the same object. I just copied and pasted it to the other side. Okay. So first things first, we have to identify the center of curvature. You can see that center point. So we'll go ahead and label that. And the distance between the center of curvature and the mirror is the radius. And we can go ahead and use that information to help us find the focal point if it's not given. Focal point, remember, is 1/2 of the distance to C, or 1/2 the radius. So we can put the focal point here, and the distance between the focal point and the pole is the focal length. All right, so now we're going to go ahead and draw our rays when it comes to a convex spherical mirror. This is a little different, however. Okay. Because it's a mirror, remember that the rays bounce off. They do not pass through it, they come back away from it. So if I draw my parallel ray coming in, it's going to bounce off as if it's going through the focal point. So you'll want to line up your focal point and then send your ray back out. Well, now you should be able to see right away that this is not going to work in terms of producing an image the way we did in the concave spherical mirror. With the concave, all of the light rays bent together and converge to a single point. This, however, is a diverging mirror. So we have to do things a little bit differently. Now, when you're drawing your ray and bouncing it off away from the mirror, what I'm going to ask you to go ahead and do here is called back tracing. So you're going to continue that line just as if it did go through the mirror, but instead of making it solid like we did here, let's make it dashed and run it back out through the focal point. Okay, and we're going to do this for all of our light rays as we do the same sort of thing that we did when we looked at the concave mirror. All right, so next one, we'll go ahead as if we were going through the focal point. So line one head with the top of the arrow and the other part of your protractor or ruler with the focal point. We go ahead and draw it in. It bounces back out parallel. And then I'm going to back trace my parallel ray. Okay. You'll notice now we've got a point at which the two come together. And if you're really confident in the work that you did, that could be enough, but it's always a good idea to do at least 3. The next one I'm going to go ahead and do is if it's going through C. Remember, it will bounce and go straight back because it's perpendicular to the surface at that point. But then we still want to do our back tracing, okay, as we go ahead and go through. Now again, those lines, if you do everything perfectly, should go ahead and line up, giving us the position of our image. All right. Now we should go ahead and take a look at those things you should be able to know when you complete a ray diagram. Those are going to be, you should know the location, you should know the size, you should know the orientation, and you should know the type. In this particular example, the location is inside of the focal point. Our size is diminished. It is smaller than the original image, than the original object. Orientation, unlike the last one we did, this one's actually upright. Remember, for the other one, we were dealing with inverted images. And then the type, notice that these are all dashed lines. These are not actual light rays because the actual light rays bounce away from the mirror. So in this particular instance, this is what we would call a virtual image because those are not real light rays that are converging together. Okay, so those are the basics of how to draw convex spherical mirrors. We did concave spherical mirrors earlier in the video, and the process is basically the same. We have 4 rays we can potentially draw, one that comes in parallel and then goes out from the focal point. We have one that goes in towards the focal point and then out parallel. And then we have one that comes in as if going through the center of curvature and straight back to the point because it's striking the mirror perpendicular. Those 3 should be enough, but if you're unsure, we can always go ahead and go through the pole and then bounce straight back out. And when you go ahead and do that, angle of incidence equals angle of reflection, and you have a 4th ray. And you could even do that here with our convex spherical mirror. I won't do it today, but you get the concept. You still would have to backtrace with it, but you get the idea. All right, so what have we learned? So we've got a couple of rules here. If you can learn these patterns and the steps in the process, it's really not that hard. And you can actually apply this to any situation with the object anywhere with respect to the mirror. If it's a concave mirror, as the object gets closer to the mirror, the image gets farther away and bigger, so its size increases. It switches from being inverted to upright when you are inside the focal point. This is something we tried to look at when we were doing our demonstration with the spoon. Okay. With a convex mirror, you're going to have to do that back tracing, and it's always going to be between F and the mirror. It will always be upright, it will always be diminished, and it will always be virtual. Okay. All right. Hope that was helpful to you guys. Please hit me back if you have any questions. Take care of yourselves, stay healthy, stay safe, and I'll talk to you soon. All right, so long.